Alrighty, we are going to do some example problems for L'Hopital's rule. So finding the limit of certain functions that fit L'Hopital's rule. And our first problem will be that we're going to take the limit as x approaches 1. Scratch that. X approaches 0. Okay. Of 1 minus cosine x all over x plus x squared. Okay. Now, the first thing we can do is, kind of plug in 0 basically. Cosine of 0 is 1, so 1 minus 1 is 0. So the top goes to 0, and 0 plus 0 squared is 0. Okay, so this thing has an indeterminate form. It's we can't really calculate that, obviously. So one thing you can do, and I highly recommend you do this for all of these problems, is you go to your calculator, plug in this function, make sure you use parentheses around the entire numerator and entire denominator, and plug that into your calculator and trace very close to 0, like 0.0001 or something like that, and see what you get. And then whatever it looks like the answer should be, now you have something you're aiming for. So once you do the L'Hopital's rule method, then you can decide whether or not you got what you expected. So it helps you to know whether you're on the right trail, right track or not. So this has indeterminate form 0 over 0. So L'Hopital's rule applies. So this is going to be equal to the limit as x approaches 0. This is a 0, not a sigma or anything like that. Of the derivative of 1 minus cosine x. So the derivative of 1 is 0. The derivative of cosine is negative sine, and there's already that negative, so that makes it positive sine. Okay, and the derivative of x is 1. Derivative of x squared is 2x. So we take the limit as x approaches 0 of sine, which is 0. Okay, and 1 plus 0 is 1. So what's 0 over 1? Well, it's 0. Okay, so that's our answer. All right, and of course, if you trace either of these two functions, that should be pretty clear. Okay, let's go on to a slightly more involved problem here. Okay, we're going to do the limit as x approaches 1. Of ln of x, the natural log of x, minus x, plus 1 over x squared minus 2x plus 1 as well. Okay, now let's take the limit as x approaches 1. Ln of 1 is 0. Minus 1 is negative 1 plus 1 is 0. Okay? X squared is, 1 squared is 1. Minus 2 is negative 1 plus 1 is, again, 0. So this thing just automatically right away fits L'Hopital's rule. So we take the derivative of the top and the derivative of the bottom. So we're going to take the limit as x approaches 1 again. Derivative of ln of x is 1 over x. Derivative of x is 1. Derivative of 1 is 0. And then we have derivative of x squared is 2x. Derivative of 2x is 2. Okay, so now we plug 1 in again. 1 over 1 is 1, minus 1 is 0. 2 minus 2, also 0. So this thing's it's still indeterminate, but this new function that we have, this new limit that we're taking, also fits L'Hopital's rule, so we can do it again. So the derivative of 1 over x, and the best way to think about 1 over x is that 1 over x equals x to the negative 1. So the derivative of x to the negative 1 is negative x to the negative 2 minus 0, because the derivative of 1 is 0, all over 2. Okay? Now we can plug 1 in, and negative 1 to the negative 2 is just negative 1, and 2 is just 2. So the answer is half. And of course, if you'd have plugged in this original equation into a calculator and traced very close to 1, you should get negative 0.5. Okay? All right, we're going to do one more problem, and this will be a much more difficult problem. We're going to have to use some logarithmic techniques here. Okay, so we're going to take the limit as x approaches 0. Limit as x approaches 0, and we're actually going to do the limit as x approaches 0 from the right, of sine of x to the sine of x power. Okay, so you have sine of x being raised to the sine of x. I'm not 100% sure why we need it to be coming from the right, but maybe we'll figure it out as we go. Or maybe if we look at it on a calculator, we'll see why that would be obvious. It may be, there may be an asymptote coming from the left or something like that. Okay, now, when you take the limit as x approaches 0, sine approaches 0. So we get 0 to the 0, which is in one type of indeterminate form. So we can't compute it, right? We can't just plug in 0 to the 0 and see what we get. It doesn't work. So we need to change this thing around and see if we can use L'Hopital's rule or something like that, or just whatever we can do. We may need L'Hopital's rule. What we do in these cases is we need to get the exponent out of the exponent. Right? We need to get the whatever's in there down in front, and we can do that with log properties. So we need to take the log of both sides. So in order to take the log of both sides, we need another side of this. So we're going to say this equals L, this whole equation. So L is the thing that we're looking for, right? That's our answer, okay? We're going to take the natural log of both sides. So we're going to have ln of capital L equals the natural log. And the natural log, we're going to take the natural log of both sides, but it doesn't matter where the limit is. We can put it inside the limit. So we're going to do the limit as x approaches 0 from the right. The natural log of sine of x to the sine of x, okay? And then we can use log properties. So it's still the limit as x approaches 0 from the right of sine of x times the natural log of sine of x. Okay? Now we don't have that exponent to worry about. And what we can do, this is just, sine of x is still 0. So natural log of 0 is undefined. So we haven't really solved our problem yet. We haven't made this any more manageable. But what we can do is we can say, well, we know that cosecant, not cosine, cosecant, okay, of x is 1 over sine, right? And so therefore, 1 over cosecant equals sine of x. And what we can do is we can take out that sine of x that's in the front and replace it with cosecant, and that gives us a fraction. So let's see how this works. We have limit as x approaches 0 from the right of natural log of sine of x over cosecant of x. And this probably has to do with why we're coming from the right. We're looking at cosecant. As cosecant, actually, yeah, both of these need to be coming from the right because both of these are asymptotes. The natural log, basically, as x gets closer to 0, sine of x gets closer to 0. And so, the natural log function looks like this. Okay? And so as we get closer to 0, we're going down that way along this. So the natural log is headed down to negative infinity. Okay? And let's see. Cosecant is going to positive infinity. Cosecant is 1 over sine. So sine is going to 0, and so cosecant is going to positive infinity. And the sine notwithstanding, this is basically infinity over infinity. That's an indeterminate form. And so now this thing fits L'Hopital's rule. So we can now take the derivative of both sides. So we're going to get the limit as x approaches 0 from the right. The derivative of 1 over sine of x is, ln of sine of x is 1 over sine of x times cosine x, right? And then the derivative of cosecant is cosecant x tangent x, right? Sorry, that's not right. It's negative cosecant x cotangent x. Okay, so this is our function. We've done L'Hopital's rule. We take the derivative of the top and the bottom. Now, we can actually simplify this. We can rewrite it. Limit as x approaches 0 from the right. Cosine over sine is cotangent. So we have cotangent over negative cosecant x cotangent x. So the cotangents cancel, and we just get negative cosecant, which we know cosecant is, what we really have is this. We have 1 over cosecant, which is equal to sine. So this has all become equal to the limit as x approaches 0 from the right of negative sine of x. Okay, and now we can do, as x goes to 0, sine of x goes to 0. Okay, now that's not our answer. We have to go back and remember that that 0 is all equal to this, the natural log of L. So what we have, if we rewrite everything, we have ln of L equals 0, right? Well, we need to solve for L. So remember, this is log base e of L, and so that means that e to the 0 equals L, and so L equals 1. There we go. Little interruption there. But that's the answer. The key here is, we took the natural log of both sides, brought the exponent down, reformed it into a fraction, right? Right here, we have our fraction so that we get infinity over infinity. And then we take the derivative of the top and the derivative of the bottom, right? Here and here. We simplified that so that we got a nice, easy negative sign, which goes to 0. And then the last step is we had to solve to get L, because we had reformatted our problem to be natural log of L, and so we had to solve that for L at the end. Okay, so these problems are a little bit long, lots of steps sometimes, but not too tricky. All right, there you go.